about typical types of components of those three categories. First, the ion sources. Historically, the first sources, and still today, arguably up there near the top in terms of widespread use, are so-called electron ionization sources. You might hear the term electron impact, and it's the same components. We're talking about the same kind of technology and the same phenomenon. It's just that term electron impact has fallen out of favor. You know what that means? It's fallen out of favor in the scientific community because formerly it was thought that there had to be actual collisions between the electrons in the electron ionization source and the analyte molecules in order for the process to take place. But nowadays, like the widely accepted theory is that that contact is not necessarily required. Yeah, I found actually a pretty nifty. I've been doing some animation and simulation searching for you guys. I have a few of them inserted here. That's why I'm going through this. You might have noticed why is Flowers doing the PowerPoint today instead of the PDF version of it, because I inserted a couple of links that hopefully will be helpful. But I found a really nifty mini lecture that I was thinking about forcing y'all to listen to in my absence on Monday, but I decided against it. You know, I'll give you the link anyway if you like, but the guy is just really way too much into the billiard ball analogy, talking about playing pool and collisions and contacts. And so, anyway, how about this? Imagine that you can get your analyte up into the gas phase. So you have gas phase molecules. They encounter this high energy electron beam. You've got a stream of electrons generated by passing a relatively high current through a thin wire filament, right? Across the ionization zone is an electrode at a very high positive potential that will basically extract electrons flowing through this hot wire filament, generating that stream of electrons, going left to right in this image the way it's depicted. Everybody good? We're generating, what's the word? A stream of electrons, relatively high energy. They are being emitted by this filament, attracted to this trap electrode over on the right-hand side. Our gas phase molecules are introduced somehow to this region. Let's just say through some sort of an inlet that's normal to the plane of the screen here. In come the gas phase analyte species, labeled M here. And by this electron ionization process, they interact with that high energy electron stream in the process becoming ionized. The most common ionization process is one whereby the analyte species lose a single electron. They become monovalent cations, right? 1+ charge. Much lesser probability that there are other ionization reactions going on. For example, forming a dication using 2 electrons. But the predominant process for sure for electron ionization of gas phase molecules is the loss of a single electron. So these gas phase cations are produced. Also, depending on the nature of the molecule and the energy of the electron beam, it could be that enough energy, more energy is transferred, not just enough to strip off a valence shell electron and form that molecular cation, but it could be that enough energy is transferred to actually rupture one or more chemical bonds, right? Breaking bonds in the molecules, yielding what we call fragments in mass spectrometry, symbolized by the F here. Those fragments likewise possessing a positive charge, very often monovalent, usually just the +1 charge, or the 1+ charge, I should say. Everybody good on the production of ions now? So inside this, oh, yes ma'am, go ahead.
So the M is crossing through the electron stream. And
not on purpose.
okay.
They're just up there in the gas phase. We introduce gaseous molecules to this ion source, right, in this vicinity right here. And they're diffusing around, and they're going to encounter the beam. Oh, don't get me wrong, it could be that we introduce them, you know, by flowing in the gaseous molecules at a certain velocity, and we can certainly point the output of our inlet towards the electron beam itself. But basically, you got gas phase molecules in the same vicinity, right, same region of space as these high energy electrons. So they'll diffuse around and they'll encounter that high energy electron beam and become ionized.
So why are the electrons stripping an electron from the NY? That's what I'm not understanding. Is it the energy of the electron stream kind of, it's bumping the electron off of the molecule?
I appreciate you wanting to have a better feel for it than
Okay,
just
so-
accepting what I'm
okay.
saying. So, yeah, here comes the molecule, right? And what do you see up there? I mean, the nuclei of the molecule, very dense, embedded in a much more voluminous cloud of electrons. And right there near the periphery, or rather at the periphery, defining the periphery, are the valence shell electrons, the ones least tightly held. So imagine here's this big puffy valence shell electron cloud for some molecule, and here comes a high energy negatively charged electron, and it's a near miss. No. Right? High energy electron near miss. Can you imagine the repulsive forces? Likes repel, right? Negative charge. Negative. It could be that miss is near enough, that energy of the electron zipping by is fast enough that it just blows off an electron. Can you think of it that way?
Yeah.
Excellent. Did I make an analogy that spoke to you? Are you recording this?
Yes.
Did that analogy speak to you? And I don't get me down into the nitty-gritty physics, because that is beyond my knowledge base. But that's the way I've always thought about it.
And I see why they called it electron impact. They were assuming that
Yeah, I mean, originally it was thought that the electrons actually have to collide, but no, they don't have to collide. And how's that been determined? I don't know. I'm unaware. Ignorant of the history, I'm sorry. Yeah, a physical analogy, people with hats. Right? The people are the molecules, their hats are the valence shell electrons, and you're standing by, a subway rail, or just the side of the road, these big semi-trucks come by, and the wind can blow your hat off. So that those electrons streaming by can blow off an outer shell electron. And hey, it could be that there's so much, it could blow off your arm, you might fragment. Ooh, now we're getting kind of
Also the F's are fragments.
It could be an impact. What's that?
That's what the F's are, but.
Yeah, the F's are fragments. I said that. Yeah, symbolized by an F there. I know that I did. We could go to the tape. So everybody good. You generate ions. And now where are these ions? They're inside this ion source. And check it out now. From top to bottom, as depicted here, we have some electro-optics. It's a general term. Here up top is an electrode. It's called the repeller electrode. It's held at a very high positive voltage. Positive voltage repelling cations in, correct? And down at the bottom of this figure, focusing lenses, they're electro-optic lenses, right? It's sort of like an exit slit. You can think of that one because that is definitely where the ions might exit, held at a high negative potential. So there is an electric field, positive up top, negative down bottom, serving to accelerate by strong migration, the cations that are formed downward. And most of them will probably strike the walls and be annihilated, but some of them will exit through a little slit in the focusing, and also, it's not called it here, but there is, a lot of these are accelerating electrodes. So the ions, the cations that are produced, are accelerated out of the source by this large voltage, this large potential field that's generated between the repeller and the focusing / accelerating electrodes. And out they come, boom. Everybody good?
So you have a stream of positive charges? Is that what you?
Say again?
You have a stream of positive charges then, or moving?
Yeah, you are ejecting the cations that are formed, the gas phase cations that are formed, the intact molecules that have been ionized, and their fragments. So the cationic species are ejected. They exit with a kinetic energy that's determined by the accelerating voltage. Right? EV, where E is electronic charge and V is the voltage applied across the repeller focusing / accelerating electrode system. Right? That determines the kinetic energy. So all the ions that are ejected have essentially the same kinetic energy. Oh, they might be a little bit different because they're in here diffusing around, correct? And it could be at the moment of ionization when they acquire the charge that makes them subject to that electrostatic ejection. Imagine some molecules might be diffusing in the opposite direction, some diffusing in the forward or downward or outward direction. So there'll be a slight spread of of kinetic energies. But 1/2 mv squared, that's just the classical physics definition of of kinetic energy. correct? Great. So what determines the kinetic energy? The accelerating voltage applied. Ions of different mass then will be traveling at different velocities, will they not? Yes, they will. All right? All the ions are ejected with roughly equivalent kinetic energies, then that means the velocities will be inversely related to the square root of the masses. So this is now well, this is one of our links. This could be a link. The ionized molecules and fragments are ejected with essentially equivalent kinetic energies as determined by the parameters of the ion source. But that means they come out moving at different velocities depending on their masses. Everybody good? Well then, good. Here's a question for you. How about calculating the speed at which a benzene ion is ejected from an ion source when the accelerating voltage, as most people call it, is 10,000 volts, 10 kilovolts? You could do the math on that. You may be expected to do the math on that at some point. You will encounter, as you almost always do, an issue with units. Be careful with the units here. You want to calculate a velocity. So that's the square root of 2eV over m. Great. 2 I'm good with. E, what is that? That's electronic charge. Coulombs per what? Just coulombs, right?
Yes.
And what about V? Voltage. A volt, by definition, you guys might be aware, is a joule per coulomb. Great, now I've got a joule. You're aiming to calculate a velocity, everyone, so we need distance over time, don't we? Where the heck's that coming from? Well, thank you. No, it was a perfect commentary.
I see. Joules are Newton meter.
Great, we got to keep scooping that. Right? A joule is a Newton meter. Great. Well, there's your distance meter.
Yeah.
And we got mass now in the denominator. Oh no.
Force is
Can we do work?
mass over acceleration. Yeah, mass times acceleration. So then you can derive the speed out of acceleration. It'll cancel out. So you have m over s. Right?
You got where'd the time? I missed where the time came in. You're heading in the right direction. You got the shovel. You know you have to dig, and I heard you get to Newton meters, and then.
And acceleration is seconds squared. So when you take to the 1/2 power.
Acceleration.
Yeah.
Where'd that come from?
Oh, force is.
It happened up there in Ms. Tyson's head, but it didn't come out of Ms. Tyson's mouth. So yeah, right, exactly. So you guys are going to need to dig down to the base units, right? All those derived units we use for the fundamental physics or physical properties. Dig down, make sure the units are good to go, and be amazed at the rapid speed, at the rapid exit, right? Check out that velocity and see. If you have any trouble, of course, get in touch and I'll see if I can help. I'll certainly try to. So electron ionization, very common, requires that the analyte species be gas phase molecules in order to be subjected to this ionization scheme. Something very closely related is called chemical ionization. It's got the same basic hardware, everyone. The same basic hardware. You have this. You have the electron ionization source, but you introduce two things, not just gas phase analyte, but also a much larger pressure or